All right, so we're given this van. It's initially smushed against this spring. So look, when the van starts out back here, what type of energy do we have? It all starts out where? Potential of spring. There's energy in that spring. Then the van shoots off the spring. The van goes like this. It goes up through the loop-de-loop, around like this. It's a, huh? Well, hey, given the fact the mass of the van is 0.1 kilograms, it's a toy car. It's a toy van. Okay, it's like a Hot Wheels track. It's a Hot Wheels track. Okay, look, the key thing in this problem right here, it says it moves without friction, right? Without friction. So the only forces affecting the motion of the van, notice that it's spring and gravity. Like, so what affects the motion of the van over here? The spring, right? The spring gets the van going. Look, now as the van goes through the loop-de-loop, what affects the motion as the van goes up this loop? Gravity, right? So we pretty much, and there's no friction, right? So what this means, guys, look, the mechanical energy at every point is going to stay the same. Does that make sense? You know, we've been talking about this. Mechanical energy at some initial point equals mechanical energy at some final point. So look, point O, point A, point B, point C, point D. All of these points, assuming no friction, what do all of those points have in common? The same mechanical energy. Now, would this happen in real life? No, because in real life we have friction, right? But here it's a physics problem. Okay, so no friction. Let's solve this. All right, they tell us the mass of this van. We know the mass. It's 0.1 kilograms. We're given the spring constant. That's going to come in handy later. The spring constant is 200 newtons per meter. What else do we have? Oh, when the van is up here at point D, when the van is up here, it has a velocity of 2 meters per second. And I think that's it. And it starts from rest, right? Before the van is released off the spring, starts from rest. Now, number one, if the level OA has been chosen as the reference level, I call it the 0 point. Mr. McGehee wrote this. So what does he mean by reference level? That's the 0 point. So he's saying OA, so this right here, this level right here, down here, this is our H equals 0. Okay? So what is the mechanical energy of everything, of the whole problem? The only point where we have enough info to do this, the only point is point D up here. So look, like, why could we not use this point? Why couldn't we use point O? Because we don't know how far the spring was smushed, right? We don't know how far the spring was smushed. Why could we not use point A? We don't know the velocity. Same thing with point B. We don't know the velocity. The only point where we know everything is point D. All right, so focusing on point D, focus on point D. What are the two types of mechanical energy? Remember, mechanical is basically kinetic plus potential. So what type of energy do we have up at point D? Does the van have kinetic at point D? Yes. How? Because it's moving. Does it have potential of gravity? Yes, because it's above the 0 point, right? The 0 point is down here. Okay? It's above the 0 point, so it has potential. And then is there any spring up there? No spring, so don't even worry about it. All right, so you go 1/2 mv squared plus mgh. So 1/2, the mass is 0.1. Velocity is 2. And then plus mgh. I'm coming down here. 0.1. Oh, use gravity is 10. Guys, I forgot to mention that. Use gravity is 10. Then h is 0.8. Okay? You add this all up. Punch this into your calculator. All of this equals 1 joule, which is the answer. That make sense? So dudes and dudettes, just check it out here. What's going to be the the mechanical energy total at point B? 1 joule. What's going to be the mechanical energy total at point A? 1 joule. What's going to be the mechanical energy total at point C? 1 joule, because there's no friction, right? If there were friction, then the energy, you know, as the van went through the track, it'd be losing energy. But there's no friction, right? It says no, right here. It says without friction, okay? Yo.
So even when it goes around the loop, does gravity not act on it?
No, it does. As it goes through the loop, what happens to the velocity? As the van goes up, 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 what happens to its velocity? It goes down. Basically, as the van goes up the loop, it loses kinetic but gains potential.
How do you account for it?
Ooh, let me show you. In fact, let's see.
Isn't that what you're supposed to do?
Let's see. Well, okay, number 2. Well, number 3 is top of the loop. Let's do number 2 first. Okay, number 2, what is the kinetic energy of the van at point A? Well, look, what do we already know about point A? So we're focusing on point A. We know that the mechanical energy at point A must be what? 1 joule, right? But what is it? What's it equal to? That's going to be, that 1 joule is equal to what? What's the only energy it has at A? It's only kinetic, right? Why is there no potential at point A? Because it's on the 0 point. So guess what? The kinetic at point A is 1 joule. That's the answer. You get it? All right, number 3. What's the speed of the van at point B? Well, dudes, focusing on point B, what's the mechanical energy at point B? 1 joule. It's 1 joule. Well, what's that equal to at point B? Well, if you look at point B, as the van is upside down right there, what type of energy does this upside down van have? Well, it's got potential because it's above the 0 point, right? It's above the 0 point. Oops, not equal. Don't put equal there, Spaldo. No equal yet. And it also has what? Kinetic. How do we know it has kinetic? Because it's moving. Okay, so basically here's our equation, right? Right there. So take this over here. Ready? We're going to go 1 is equal to mgh, right? That's for potential, plus 1/2 mv squared. So let's plug in. So 1 is going to equal, so m is 0.1, g is 10, h is what? 0.5 plus 1/2 0.1 v squared. Guys, what's the only thing missing in this equation? V. So solve that for v. You get square root of 10. All right. I think that's good for today. Alicia, I'm going to post this. Yep.